For many years, bridges of all shapes and sizes have been a vital part of our lives. Whether it is a part of a roadway, railway, or even a pedestrian walkway, a bridge provides a direct pathway over otherwise impossible to cross terrain such as lakes, rivers, harbours, or canyons. These bridges are designed with careful consideration as to the specific purposes required, as they must not only endure their self-weight, but also an additional live load such as pedestrians, traffic, trains. This assignment requires students to separate into groups and carefully design and construct a bridge made from spaghetti and superglue. The bridge is to weigh no more than 200 grams while having a 350mm span or greater and being no more than 80mm wide. In the design, it must also be considered that the section in the middle must accommodate the hook platform which applies the load. The bridge that can withstand the most load in comparison to its weight will be the winner.
There are two designs where we went with truss-type bridges. Truss-type bridges are very common in the modern age due to their nature. Some characteristics that they generally conform to are, they have a rigid structure, they contain mostly empty space, they have members in either tension or compression, and they are made up of connected elements in triangular formation.
Truss bridge types have many different advantages and disadvantages over other bridge types. The advantages are that they have high load bearing capabilities in comparison to their weight, they use materials effectively which makes them economically viable, and since they are mostly empty space, they don't have to worry as much about wind loads. The disadvantages are that they are quite large in comparison to other bridge types due to them being mostly empty space. They have quite high engineering requirements, and lastly, they have many different parts that need to be manufactured.
The first bridge design that was chosen was a modified 3-panel Howe truss bridge. William Howe designed this bridge type in 1840 and it was predominantly used on railway bridges. Howe truss bridges typically have diagonal members in compression and vertical web members in tension. The rationale for using the Howe truss was to have a simple, strong and lightweight bridge. Our first bridge weighed 52 grams.
Okay, so 1 kilo. Ooh, that was a big one. That was
Keep going anyway.
Yeah, this one is not doing well at all. Our initial Howe truss only carried 1 kilonewton. Our final design was the K-truss. The K-truss was initially designed by Phillips Johnson in the earlier 20th century. It uses additional diagonal members to help reduce the compressive load in vertical members. This is beneficial due to the fact that spaghetti is weak in compression but strong in tension. Along with the truss changes, additional cross-bracing within the base was included, along with a thickened bottom cord. The weight of this bridge was 111 grams.
Yeah, you have video presentation. Okay. So that's to do a report. Now I think we do report and video presentation.
Ooh, starting to.
Oh yeah, try to stop that. Good.
Still good.
I'll still drive over it.
That's fine. It's the glue.
But you let it go until it just full on. Should fall out through it.
Just do a drive over it.
Alright, no, I reckon that's where you'd stop.
Yeah, it's gone back down.
This truss design carried 5 kilonewtons.
For the initial bridge design, our bridge weighed 52 grams and supported 1 kilonewton of force with a strength to weight ratio of 1 to 52. The second K-truss bridge weighed 111 grams and supported 5 kilonewtons with a strength to weight ratio of 2.34 to 52. As it can be seen, there has been a 134% increase in load capacity, so it can be easily stated that the second bridge design is more efficient.
Throughout the design process, we learn how compression and tension members react to external forces and how the placement of these members and their size can dramatically strengthen or weaken the integrity of the bridge. Our first bridge design didn't support much weight at all, but as we revised the design and made adjustments, we were able to significantly increase the weight you can carry. In our testing, we found that it wasn't the actual structure that failed first, usually, but the points that the members were glued together. If we were to do this assignment again, we would focus on these points, potentially adding more glue to avoid failure. This assignment has helped us to gain a much greater understanding of what it means to be a structural engineer, helping us go through the 3 design stages of designing a truss, being working out loads that we'll need to carry, analysis of the loads in members, and choosing what sections we use for each part by gluing together strands of spaghetti. Thank you for viewing our presentation. We hope you found it informative and interesting. Hey, it's Jesse.
Corey here.
George.
This is Group 13 signing off.